next big step, giant step that Newton took, and this giant step, by the way, is composed of many parts, which will almost consist of the entire rest of the lecture, is that the force of gravity goes according to this law. Now, what does this law mean? It says, suppose you have two masses, m1 and m2, any two masses, okay, Earth, Sun, two objects, two students, anything, okay? If you have any two masses, then there is a force of attraction between them, which we call gravity, and the value of that force is given by the mass of these two bodies, multiplied the two together, and divided by the distance squared, multiplied by a constant, okay? Now, Newton figured all of this stuff out from using Newton's law, F equals ma backwards, okay? And what I'm going to do now is I'm going to show you how Newton went step by step to get here. So I wanted to show you the end first. This is the end of the lecture. Then in the next lecture, I will apply this to show you how Newton used it to calculate the motion of tides or the shape of the Earth in more exact detail and so on. All right. So Newton's law of motion. Now, the other part of this I want to impress upon you is that Newton's second law of motion and Newton's law of gravity together reveal the entire working of the universe. Okay, namely, all the motion of the heavenly bodies, all the motion of objects on Earth. Okay, and some people say, oh, it's God's design in two equations. Okay, so what I'm going to now explain to you is how he got there. All right, now this is really a very important point in this course because it brings to a climax everything that we'll be talking about. Okay, so you'll see that in order for Newton to get to that law that I put up there, we will use all of this stuff together. Namely, Newton relied on all of this, namely Pythagoras' idea of symmetry, number patterns, elegance, and beauty in nature, Aristotle's creation of the idea of gravity, Eratosthenes' attempts to measure the size of the Earth and the distances to Earth, Sun, Earth, Moon, Archimedes' ideas of density, volume, all of this stuff I've taught you, little by little, it's all going to come together now into this law, okay, this one law. Copernicus' sun-centric system, Galileo's discovery, Brahe, Kepler, all of these are going to come in and I'm going to show you where, okay? But it's all synthesized. That's why we call this the synthesis, right? So this is the synthesis. All right. So we'll start with Galileo. It won't be in order, okay? It'll be in different places, but I'll point it out. So we'll start with Galileo's observations. Of course, it was based on, stimulated by Aristotle, but of course it was Galileo's observation. And Newton used it to determine, as a first step, a new property of the gravity force. Okay, remember, he was using motion to figure out force. So I'm going to show you what he used, how he used this behavior to figure out a new property of the force of gravity. All right. Now I'm going to do a demonstration which I call the donkey demo. Okay. I don't have a donkey here, but I'm going to pretend as if I'm the donkey, all right, and I'm going to have a cart that's moving, and I know what, I should have asked for a fan cart, but never mind. So suppose I pretend that this object, I give it a little force, and now it's accelerating. And suppose I'm able to produce this force reproducibly to show you the acceleration each time, okay? And suppose that my fingers are such that I provide the maximum amount of force, okay? Namely, I'm pushing as hard as I can, okay, on this object. So the donkey is pulling a cart of hay, and he's pulling as hard as he can, okay? All right. So now you memorize what acceleration I'm getting, all right? All right, now I'm going to take these three masses and I'm going to put them in here, okay? On top of this cart, okay? And I'm going to again apply exactly the same force. Now I can't do it exactly, but I'll get close to it, right? And what's going to happen to the acceleration? What will happen to the acceleration when I apply that force? it's much less, right? Because it's the mass, right? According to Newton's law, acceleration drops if I raise the mass. Okay. Now pretend that the Earth is a donkey that is pulling on this object. All right? So here we go. Acceleration is how much? You know the number. 9.8 meters per second squared. All right. Let's double up the mass. What's the acceleration? Huh? No, forget my hand. Here, let me drop it. What's the acceleration? Galileo's experiment. What's the acceleration? Now hold on. Now how come the donkey applied his maximum acceleration, and when I increased the mass, the acceleration slowed down? And when I do this with the Earth, the acceleration is the same. What's wrong with this donkey? See, this is what Newton was thinking. What's so special about this donkey that it knows that I increased the mass, and now it adjusted its force to increase the acceleration back to g? Right? So, the real donkey is gravity. Okay? And what Newton deduced from this, which you probably have already deduced now, right, is that when you increase the mass, the acceleration remains the same for gravity, which means, this just like Galileo showed at Pisa, but of course Galileo couldn't explain why these two accelerations are the same. And what Newton figured out is that this property of Galileo's tells us something about the gravity force. And that is this, opposite. The gravity force has a special property that if you add more mass, the donkey pulls harder. Right? The Earth, the donkey pulls harder. But we know that gives you a special, case. And the special case is, according to Newton, the special property, I mean. And the special property what Newton isolated, or put his mind on, is that the Earth's force of gravity on the apple is proportional to the mass of the apple. Right? It's like the donkey says, oh, you're going to give me twice as much weight? Well, I'm going to pull twice as hard. All right? So the force of gravity depends on the mass of the object that it's acting on. Really strange force. Okay? That's the property that Newton figured out. And so if you replace this proportionality constant, if you replace this proportionality relationship by a constant, then you get force of gravity is a constant times the mass of the body that it's acting on. Why the Earth decides to apply its force of gravity and adjust it according to the mass it's acting on, we don't know. Newton couldn't figure that out. But Einstein did figure it out later. That's the theory of general relativity. Okay? Newton didn't know that. But he figured out at least this property. He took the next step beyond Galileo. Because Galileo said the acceleration is the same. But now Newton is saying, if the acceleration is the same, it means that the force increases with mass, okay? The mass of the object. Now you apply Newton's law to this law, okay? So you got F equals ma for the two objects, and F of gravity equals km. If the mass is m, then you put ma equals km, get rid of these two forces, cancel out the m's, and the acceleration is a constant. That's the constant of the acceleration. So basically he's explaining Galileo's law, which you already understand now, that if the force increases, the acceleration will be the same. So the force of gravity has a new property, which Newton discovered by this just simple thought process. And I'll show you more of his great accomplishments with these simple thought processes. All right. So the acceleration is constant. Constant acceleration of motion from Galileo revealed this new fundamental property of gravity to Newton, that the force of gravity is worth repeating. The force of gravity is proportional to the mass of the body that the force is acting on. Okay. Somehow the thing figures out, what you're going to do? I'm going to increase my force. Okay. It's very strange, but that's the way gravity is. Okay. By the way, it's different from F equals ma. F equals ma just tells you that if you have a certain force, what will be the acceleration. Okay? And here you see I've applied both F equals ma and this property of gravity to figure out that the acceleration is constant. All right. So that was his first inspiration that leads to this grand law. Okay. Now I'm going to talk to you about his second inspiration. But first I need a little drink. So, all right. So, the question that Newton asked is, all right, here's the Earth, and it exerts a force of gravity on objects on Earth. How far up does the force of gravity extend? Okay. So I'm going to give you a poem of Alfred Noyes again on this grand moment in the history of science, okay? And of course you know what it is, right? Newton is sitting in the garden at his home in Lincolnshire. And this is the poem of Alfred Noyes. It says, "Did Newton, dreaming in his orchard there, beside the dreaming Witham was the river that flowed through this town, did Newton see the moon burn like a huge gold apple in the boughs and wonder, why should moons not fall like fruit? Okay. Or did he see, as those old tales declare, a ripe fruit fall from some immortal tree of knowledge, while he wondered at what height would this earth magnet lose its darkling power? Would not the fruit fall earthward, though it grew higher over the hills and yonder brightening cloud? Would not the self-same power that plucked the fruit draw the white moon then sailing in the blue? Then, in one flash, as light and song are born and soul awakes, he saw it, this dark earth holding the moon that else would fly through space to her sure orbit, as a stone is held in a world sling, and by that self-same power, her sister planets guiding all their moons, while exquisitely balanced and controlled in one vast system, moon and planets wheeled around one sovereign majesty, the sun." Okay? So here he's capturing in this poem his entire theory of gravitation, which I'm going to explain to you. Okay? And this, by the way, is a picture of Newton's house in Lincolnshire as it stands today. This is probably not the apple tree. That apple tree's fallen down already. Okay? But actually a little bark of that apple tree is preserved in a museum in here. So he's probably sitting underneath this tree or some tree nearby here. And it's not true that an apple hit him on the head and the theory of gravity just popped out, okay? So we'll see now, okay? His intellectual journey. Going to see his journey now, okay? Okay, so the Earth, he says, exerts a force of gravity on the falling apple. And so any object on the surface of the Earth experiences this downward force of magnitude mg. Okay? Now, as I said, how far does this force of gravity extend? Does it extend all the way up to the moon? So this contemplation, this question was this pivotal event, okay? And what he figured out, and I'm going to discuss it in more detail, that if the moon goes around the Earth in a circular motion, then there must be a centripetal force acting between the moon and the Earth. Okay? Just like anything that's moving in a circle has a centripetal force that keeps it moving in a circle. Okay? And he knew this, by the way, okay, that circular motion should have a centripetal force. But he asked, could that centripetal force be the force of gravity? Right? That's the key question. Can I show that the necessary centripetal force to keep the moon in a circular orbit is the same as the attraction of the Earth? Okay? So for that, he needs to know a lot of stuff, like how far is the moon, how fast is it moving, maybe the mass of the moon, and so on. So could it be gravity which could it be the same force of gravity which attracts the apple to the center of the Earth? And is the centripetal acceleration this value, g equals 9.8 meters per second squared? Right? Because if he can get that centripetal acceleration, then he's got it, right? He knows it's got to be gravity. Okay, so he says, let's try out the numbers. So he goes into his knowledge and libraries and so on to figure out whether this acceleration of the moon is this value. And by the way, he already knew independently from Huygens that when the body moves in a circle of speed v in a radius r, there is centripetal acceleration, and the acceleration is v squared over r, which I derived for you last time. Okay? Newton had already derived that. All this while he was age 20, sitting in the, at home, told to go home from the University of Cambridge because there was a plague. Okay, and so he did all of these wonderful discoveries over here. All right, so he said, okay, let's consider how is the moon going around the Earth. Okay, so he needs to know two things: v squared over r. So the speed of the moon, right, and the distance between the moon and the Earth. Well, the speed of the moon is known from the ancient Babylonians, right? It takes 23.6 days for the, 29.3 days for the Earth, for the moon to go around the Earth. That's the month, right? So just convert that period into seconds. Now, to get the speed, I need to know 2 pi r. Okay, 2 pi r divided by 2. Okay, if I know r, at 2 pi r will give me this distance, divided by t, that will give me the speed. Okay, now he knew what the r value was, starting from Eratosthenes all the way up to Tycho Brahe's parallax measurements. He knew what the distance was from the Earth to the moon, 385 million meters. Okay, he knew that. Okay, so here's where Tycho comes in. Okay, if Tycho hadn't figured out this exact value, now the true story, I'm jumping the true story. Okay, but the true story is that Newton had the wrong value of r, and his first attempt to do this didn't come out so good. Okay, so he waited, but then when he found the correct value, he got the results I'm going to show you. So let's skip all that problem and say, let's suppose he had the right value from Tycho. And then he can calculate the speed of the moon. The speed of the moon is this distance, 2 pi r, divided by the time, which is so many seconds. All right, so I did that, and I divided it out. And you can do this with a calculator. And he comes out with 1,021 meters per second, which I put up there. Okay, 1,021 meters per second is the speed of the moon. So then in order to calculate the centripetal acceleration of the moon, you've got to take v squared and divide it by the same r. So he did that, 1,021 squared divided by r, 385 million meters, and he got this number, 0.002 meters per second squared. It's much, much smaller than the value of g. So at this time, anybody else would have given up and started selling the apples instead of trying to figure out what was going on, right? Nevertheless, so a lesser mind would have given up the idea, right? But Newton, now we're coming to Pythagoras. Newton saw a wonderful pattern in the numbers, okay? An interesting mathematical pattern in the numbers. And here again, we are talking about Pythagoras' inspiration. So let's take his answer. And he said, I want this answer, but I got this answer. So let's divide these two and say how much smaller or how much bigger is the Earth's acceleration than the moon's acceleration. And so this ratio is almost 3,600. Okay? So he saw that number. And then he said, this number, he was also a very highly trained mathematician. He sort of knew this number is also 60 squared. And that, by the way, he recognized is the ratio of the distance between Earth-Moon and the Earth radius. So if you take this distance and divide it by this distance here, you get 60. So he's saying that this ratio of the accelerations is this distance squared. Okay? So the mathematical patterns are coming up again. The moon's acceleration is 60 squared times smaller than the apple's acceleration. That's this value here. But why? Now he comes to this intellectual leap. The reason this is true is because the Earth's attractive force gets weaker as you go further with distance. And how does it get weaker? It goes weaker 60 squared times because this distance is 60. Then comes that flash, yeah? The big flash of inspiration. That generally the force of gravity goes like 1 over distance squared. Right? That's where the 1 over r squared comes into his equation, right? Into his grand picture. From here, from the moon's behavior, in trying to make this acceleration come out right, he says the force of gravity must weaken with distance. And when these distances are so large, the force of gravity is less. Okay, all of this is also explained in the book. But that gives you the next, the next part. So you would think, like Kepler, when he discovered that r cubed over t squared is a constant, he said, oh, these are the harmonies of the universe, and I have found the secret, that Pythagoras was after. He was just jumping up for joy and writing books and books about it. Well, Newton just kept quiet. Right? He did not have any of these bouts of ecstasy over this grand discovery that the force of gravity must go like 1 over r squared. So Newton had explained that the moon is actually being pulled by the Earth, but it's not falling to the Earth, but it's going in a circle around the Earth due to this centripetal force that's acting on it. Now, one of the facts that one of the problems, one of the intellectual hurdles that Newton faced in prevented him from jumping up for joy was the fact that the Earth and the Moon are far away from each other, and he could treat the Earth and the Moon as 2 points because the sizes of the Earth and the Moon are small compared to the distance between them. But the apple and the Earth are quite next to each other. So here's the picture that troubled him. So this is the Earth and this is the apple, and this is the Earth and this is the Moon, right? He can easily treat these two as two objects where the force of gravity decreases as 1 over r squared. But the Earth and the apple, how could he treat that as two separate objects? So, in order to do this, he invented the mathematics of integral calculus. Okay? And that took him several years. Okay? And after he had figured out the mathematics of integral calculus, he proved that you can take this entire mass of Earth and stick it to a point in the middle, and it'll behave the same way to the apple as if the mass were distributed over the surface of the Earth. This is a conclusion of integral calculus. Right? Now, I'm not going to go through integral calculus for you, but I'll give you the heart of his argument, okay, in pictures. So the heart of his argument is as follows. Consider that that's the apple, and consider two objects, two symmetrically placed chunks of Earth. All right? Now, this chunk of Earth pulls on the object in this direction with this vector, and this chunk of Earth pulls on this apple in this direction. And of course, he knew about vectors, and he knew that the force is a vector, and so he resolves this vector in its horizontal component and its vertical component. And the vertical component is a force towards the center of Earth. Now this guy, symmetrically placed here Pythagoras is helping him with symmetry, right? This guy, symmetrically placed here, has this vector, and you resolve that too, so now you basically have another force here, and this force here is essentially the opposite as the force here. So these two forces are equal and opposite, they cancel each other, but these two forces here are in the same direction towards the center of the Earth, and they add up. So, he says, I can now cover the entire volume of the Earth by rotating this figure round and round and round and moving and looking for symmetric objects, and I will always get the force to be towards the center of the Earth. So that gave him the, and he actually did this mathematical integral, okay, to prove that the entire mass of the Earth can be replaced by a mass of the same mass at the center. And now he could apply his law. Okay, so once he got that, he could say, okay, the force of the apple of the Earth is given by the force of all the mass of the Earth at the center with the distance of the Earth and the Moon. So just to review now, the crucial insights in understanding the motion of the Moon were that the attractive force of gravity, which is responsible for the apple falling to the Earth, is also responsible for the Moon's orbit around the Earth. Okay? The same force is acting for motion of earthly bodies as for the motion of a heavenly body. Okay? Earth and heaven are obeying the same laws. So this is not the first time that someone had perceived a unity between heaven and earth, because if you remember, Galileo had noticed that Moon has mountains. And that said that Earth and heavens have the same stuff. Now, Newton is going the next step and saying not only is the substance of heaven the same as the substance on Earth, but the laws that operate in heavens are same as the laws that operate on Earth, namely the properties of gravity. So that's his first grand conclusion. Second grand conclusion is that the force of gravity decreases as 1 over distance squared. And now that applies for the apple, it'll apply for the Moon, it'll apply for everything. And so he started to give the mathematical description for the force of gravity. Okay, so now comes the next big step. Could this force of gravity, so we know it's responsible for the motion of the Moon, but could the force of gravity be also responsible for the motion of the planets around the Sun? Okay, now that's a big step to go from Earth, Moon to Sun planets. All right?